Hello everyone, welcome back to another great section of this lovely tutorial class. Today we are going to be looking at a very important topic in physics, which is the kinetic theory of gases. The what? The kinetic theory of gases. Now, what is the meaning of kinetic theory of gases and what does it entail? What are we actually saying when we are saying the kinetic theory of gases? Now, I can still something like really recall back to our elementary physics, work, energy, and power. We say we have forms of energy, types of energy. We have mechanical, electrical, and so on. We have forms of mechanical energy. We can have potential, kinetic. So, we have first of all, we have already used kinetic to describe the type of energy. And we said that energy is a form of energy possessed by a body that is in something called motion. That's what? Motion. So when we now bring this same kinetic to gases, to look at the theory that we now call the kinetic theory of gases, we are actually saying that the studies of gases that are what? In motion. Now, we are talking about motion here mainly because we also have kinetic theory of matter, which actually was trying to tell us that matters are composed of particles that are constantly in random motion. If you look at the postulates of this kinetic theory, these planes motion are always there. They are always what? They are always there. Now, look at for the first thing we're going to do now. Before we go into this class, ensure you don't skip any part of this video. Ensure you share this video to others. Ensure you also do something for me, something very important. Like this video. Just click on that like button, the button that takes this shape. And also subscribe. Just click on subscription, that subscription button. You are not going to use money for that. You're just going to, it's just as if you are just following us on YouTube. So ensure you have done that. And again, don't distract yourself by any means. Don't skip any part of this video. Watch this video from the beginning to the end. Now, let's go back to what we are saying, the kinetic theory of gases. Now, the first thing we are going to look at now are the postulates or the assumption of this kinetic theory. Now, what are those theories that we are actually talking about? The theories are as follows, or the assumptions are as follows, that gases are composed of particles called molecules. Gases are composed of particles that we call them molecules of this particular gas. And the molecules of a gas are something like in constant random motion. The molecule of a gas are constantly in a what? Random motion. Now, the only interaction between these molecules of a gas or of these gases we are talking about, the interaction between them, there's not much interaction. The only interaction is that they collide with each other and they collide also with the wall of the container which they are placed in. No? If you want to hold the gas, you're going to place them inside a particular container. A container is something that can hold something. And the collision between these gaseous molecules, are perfectly elastic. The collision between gaseous molecules are what? Are perfectly elastic. And we have some other assumptions or postulates from this kinetic theory we should also look at. Remember, gaseous molecules are constantly in what? In random motion. They are constantly in random motion. That they are moving randomly. And the interaction between these gases mainly is collision between each other. No, and the collision between these gaseous molecules is that the type of collision we're talking about here is that a perfectly elastic collision or elastic collision. Remember, we have from collision theory, we have inelastic collision, we have elastic collision. So a collision between gaseous molecules are perfectly elastic, or they are elastic. So you also take note of that. It's very, very important. And the bombardment with the wall of the container of this gaseous molecule, if you place this gas inside the container, the molecule will bombard the wall of the container. The bombardment with the wall of this container gives rise to a particular phenomenon that is known as pressure. Give rise to pressure. Also take note of that. It's very, very important. These are examinable questions. We also have other postulates of this kinetic theory that you should also look at. Now, mainly, the first thing I want to look at, because Now, the first major thing we are going to look at this place now. The first major, we have already talked our nose into some of the postulates of this kinetic theory, and we said gases are composed of particles that are called molecules. The molecules of this particular gas are constantly in the what? Random motion, and the collision between the gaseous molecules are perfectly elastic. The bombardment or the heating of this gaseous molecule in one of this container, when it is bombarded in one of the container, it gives rise to a phenomenon that is known as what? Pressure. Now, in a distant time, we'll be looking at pressure exerted by a particular ID gas that is placed inside a cubic enclosure, or that is placed inside a cube. But for that, let's look at how gaseous molecules behave. Let's look at how gaseous molecules behave in terms of temperature, volume, and pressure constant relationship. Let's say if you have a particular gaseous molecule that has a constant temperature, how will this gaseous molecule behave? If you have a constant volume, how will this molecule of gas behave? If you have a constant pressure, how will it behave? So let's look at volume, temperature, pressure, constant relationship. Now, years back or years ago, there are some scientists that worked on this particular gas or this gas, and they discovered that in a certain time or at a certain point, if the temperature of the gas is constant, the volume is going to something like relate to the pressure in a given proportion. Remember, we have variation in mathematics, we have inverse variation, we have direct variation, joint, and so on. So this particular phenomenon gives rise to some laws according to their names. But the first one was the one we call Boyle's law. We call it Boyle's law. Now, what is this Boyle's law? Well, this was actually talking about for a particular gas, if the temperature of the gas is constant, or if maybe volume is changing, pressure is changing, but the temperature remains the same at a constant temperature, Boyle's law. Boyle's law, that is the first law, or that is the first scientist that worked on this particular gas, and he derived the law and he called it the Boyle's law. Now, what is this Boyle's law actually saying? It was trying to tell us that at a particular point in time in the gas, if the temperature of the gas, or at a constant temperature, the pressure of the gas or the volume of the gas will be inversely proportional to the pressure. It will be what? Inversely proportional to the what? To the pressure. That is PV is equals to constant. That's what it's trying to tell us. PV is equal to what? Constant. PV is equal to constant. That means the pressure of a gas is inversely proportional to volume, or volume of a gas is inversely proportional to what? To pressure. To pressure. That's from Boyle's law. That's from Boyle's law. So this is actually saying that if you have P1 times V1, it will be equal to P2 times V2, and so on. Equal to P3 times V3, and so on. And so on. So this is inversely proportional to each other. That means this and this are inversely proportional. Then the next law, in terms of time, let's be really fast so that we'll be able to do much in this regarding this topic. Now, the next law was what they call Charles' law. What they call Charles' law. That guy worked on the gas, and he discovered that at a constant pressure, the volume of the gas is directly proportional to temperature. At a constant pressure, the volume of the gas is directly proportional to what? To temperature. That means the V divided by T must be equal to constant. That's the meaning. This shows that volume is directly proportional to temperature. That's the meaning. If I say volume is directly proportional to temperature, if I remove this proportional proportionality, I will insert a constant, then T. So I can also call this one divided by T, divided by T. This will cancel this. V over T is equal to constant. That's what I'm trying to say. That's what I'm trying to say. Remove this one, you insert a constant there. So if you have something like this, V over T is equal to constant. It's telling us that V and T are directly proportional to each other. Now, what is the meaning of direct proportion? Because we have looked at inverse proportion and direct proportional. So say something is inverse proportional to each other, and something is direct proportional to each other. Now, what we're actually saying is that if it's, for example, this first one we're doing, before I go to that, this first one we're doing, If the pressure of a gas at a constant temperature, if the pressure increases, the volume will decrease. And if the volume increases, the pressure will decrease. If one is going up, the other will be going down. That is meaning of inverse proportional to each other. Now, what is not direct proportion? For example, I will say at a constant pressure, the volume of the gas will be directly proportional to the temperature. What is not that? It means that if pressure is constant, if volume increases, the temperature will also increase. That is what we're actually seeing in that place. Now, this shows us that V1 over T1 will equal to V2 over T2, and so on, and so on. So this is directly proportional or direct proportion. Now we have another one, the one they call pressure law or Gay-Lussac law. Or Gay-Lussac law, pressure law. Now the pressure law was actually trying to tell us that at a constant volume, the pressure of the gas is directly proportional to the temperature. That is P over T is equal to constant. So what? Constant. So some persons also call this one, because it was one scientist that worked on this, which is the one Gay-Lussac. So we don't call this Gay-Lussac law, but we call it pressure law. So this shows us that P1 over T1 will equal to P2 over what? T2, and so on. So if the pressure is increasing, the temperature will also what? Increase at a constant volume. This is what gave rise to constant volume gas thermometer. Constant volume gas thermometer. The working substance is the pressure of an ideal gas whose volume is what? Kept constant. Let me just remember. If the pressure is not increasing, the temperature will increase. If pressure is decreasing, the temperature will decrease. Was actually derived from this law. Because this told us that if a particular ideal gas has a constant volume, if you increase temperature, pressure will increase. If you increase pressure, temperature will increase. So that was now how we can use this one as a thermometric property. The pressure of an ideal gas whose volume is what? Kept constant. This one is what? Kept constant. Now, let's look at now if we now combine these three laws, 1, 2, 3 together, we are going to form a particular general equation. In combining equation 1, 2, 3, we are going to have the first one was P1, V1, we're going to have P1, V1, then T is always at the bottom over T1 was equal to P2, V2 over what? T2. So we are going to use this to calculate if none of them is constant. For example, if volume is changing, temperature is changing, pressure is changing, we will solve it this way. But if volume is constant, pressure and temperature will relate this way. If temperature is constant, volume and pressure will relate this way. If volume is constant, pressure and temperature will relate this way. But if none of them is constant, if none of them is something like the same, constant means it does not change. But if none of them is constant, then the relationship will now be that. Now from there now we can derive a general ideal gas equation. The general ideal gas equation now will be PV is equals to nRT. PV is equals to what? nRT. Where N is the number of moles. The number of molecules. Take note of that. We have what we call numbers of moles. That is having a unit as moles. They call it in chemistry, in practical chemistry, amount of substance. That's what we call it. And the unit is in moles. They also have numbers of molecules. That's why we have unit. And you have just like numbers. Numbers also have unit. Because we're going to be doing numbers of molecules in this place. There will also be numbers of moles. Now, numbers of moles will be in moles. Number of molecules, particles actually. It will be in molecules. So numbers of molecules. We call it numbers of particles. Some chemists do call it. So PV is equal to what? ROT. This pressure, this volume, this also this one general ideal gas derived from this place. Then from further derivation, we will obtain this equation. So take note of this, and what and this. Take note of this 5 equations for now that we have derived. Now what is the meaning of P here? P, we check everything in this place. CV is constant too. That C is denoting or for constant. Now what's the meaning of P? P is pressure. Anywhere you see P there, denotes pressure. And that pressure, I think that's the one in this place. Let me even use this one now. The pressure here must be in Pascal. Should be in Pascal. for this molar gas, because this arrow is universal molar gas constant. So take note of that. Energy P in this place actually denoting pressure. Now what about T? T actually in this place is actually talking about thermodynamic temperature. Thermodynamics temperature. And what is about thermodynamic temperature? It's a type of temperature whose unit is in Kelvin, which is the thermodynamic scale. So the unit of this T, especially the one here, must be in Kelvin. Take note of that. It's very important to do that. Then, what is the meaning of this? What is the meaning of this one? This is called numbers of moles. Numbers of moles. The unit is in mole. Moles. Not mole. Moles is not abbreviation for molecules. Take note of that. This one is the unit for amount of substance, which is moles. This one is the unit for amount of substance is in moles. We call it numbers of moles. It's the amount of that substance. Then V is volume. Volume should be meter cube. But we will see some volumes in cm. I'm going to explain it very. And then I'm talking about the one here. One in this week. For the one here, I'm going to explain it later. But this one here, this volume is in meter cube. Pressure, this pressure is Pascal or Newton per meter square. Newton per meter square or Pascal. Then T is the Kelvin, which is the dynamic temperature. Then arrow is called universal molar gas constant. That's how the universal molar gas constant. The value of arrow is actually a constant value if this unit entails or stands. If you are using this unit I just quoted, arrow will be 8.314 joules per whole Kelvin. You can see, this one is in Kelvin, it should be in Kelvin. Now, moles, very good. Then, what is the other one? Joules. Joules is in Newton. Remember, joules is the unit for what? And what is what? What is this? The Newton meters. It's Newton and meters. So, this actually essential to be Newton per meter square for pressure, so that the unit will correlate with each other. So that the unit will follow each other. Please take note of that. It's very, very, very important. Now, let me look at a particular question so that you see what I'm trying to say. Look at this question. The volume of a gas is 100 cm3 at 27 degrees Celsius. The volume of a gas is 100 cm3 at 27 degrees Celsius. At what? At 27 degrees Celsius. At 27 degrees Celsius. Full stop. If this gas is now heated to a temperature T and a volume of 120 cm3, the volume of 120 cm3, if this gas is now heated to a temperature T and a volume of 120 degrees Celsius, calculate the value of T. Calculate the value of what? Of T. Now those 5 formulas I gave you guys, which one relates volume and temperature? That V over T is equal to what? Constant. Which is V1 over T is equal to what? V2 over what? T2. Now what's our V1? The first volume there was 100 cm3. Then the temperature was 27 degrees Celsius. I told you this temperature should be what? Kelvin. So the temperature now will be 27 plus 273, which is 300 Kelvin. That is the temperature you're going to use, not this. Take note of that too. Then the second volume will determine the volume we are going to use here. The second volume is still cm cube. So we can use cm cube. Even though you combine it to meter cube, you still get the same thing. Then what will be the second temperature? To be T. So if we do this into this formula, we're going to have V1 is 100, T1 is 300 Kelvin, is equals to V2 is what is V2? 120. What is T2? What is T2? T2 is T. So if this cancel this, we will have 1 over 3 is equals to 120 over T. T times 1, just doing cross multiplication. T times 1, that is T. 3 times 120, that will give us 360. That's 360. And the unit is what? Kelvin. Now, in some auctions, some books, they may decide to bring the temperature back to Kelvin again. Since the question was in back to degrees Celsius again. Since the original question was in degrees Celsius. So if you want to move this one to degree section, what you just do, you just remove 273 from this. This one now move it to degree section. So right from Kelvin to degree sections, remove 273. So you have 10 minus just put, you know how to do this now. Or just like we don't do it, if you don't know how to solve it. You will borrow from 6 because 10 minus 3, that is 7. What will be here? Or we have 5 here now. Borrow from this, we call it 15. 15 minus 7, that is 8. Then 3, this one will now be 2. 2 minus 2, that is 0. That is 0, 8, 7, that is 87 degree Celsius. That's what you're going to have as your final answer. Now, let's look at another question. Calculate the volume of an ideal gas at STP. Calculate the volume of 1 mole of an ideal gas at STP. Calculate the volume of 1 mole of an ideal gas at STP. Calculate the volume of 1 mole of an ideal gas at STP. At STP. Calculate the volume of 1 mole of an ideal gas at what? At STP. Now, how do we solve this question? The number of mole is 1 mole. We have 1 mole. It says STP. Now, what's the meaning of at STP of a gas? STP means standard temperature and pressure. Now, what is the temperature at that standard temperature? The temperature is 0 degrees Celsius, or which is also set here as 273 Kelvin. At STP, the temperature is 273 Kelvin or 0 degrees Celsius. Take note of that. Then the pressure is 1 atm. 1 atm. 1 atm. And I said we may not use atm in this case because we are using that P physical to ROT to solve this question now. I'll show you why I'm using that. Because we already have number of moles there. That's the only equation that has number of moles there. So this 1 atm is approximately 1.013 times 10 to the power 5 Pascal. 1.013 times 10 to the power 5 Pascal. Or we can also say P is equals to 1.013 times 10 to the power 5 Newton per meter square. This is in this Pascal. I can take them as to be the same. We don't think as ATM at 1 atmosphere. 1 atmosphere is the same as this. Take note of that. 1 degree is the same as this. Take note of that. Then, what will be the volume? The volume will be what? Remember, PV is equals to N ROT. So our V will now be N ROT over what? Over what? Over P. Divided by P. So we will have our N is 1 times our R is 8.314. Remember that. R is a constant number. R is 8.314 joules per mole Kelvin. So times temperature. The temperature is 273 over the pressure is 1.013 times 10 to the power 5. So if you solve this your calculator, 0.0224 meter cube. That is the volume occupied by a particular 1 mole of a particular ideal gas at STP. Now, you do this for me. Do this for me. Calculate the volume occupied by an ideal gas. Calculate the volume occupied, or calculate the volume of an ideal gas. Calculate the volume of an ideal gas. Solve this question for me. Calculate the volume of 10 mole of an ideal gas. 10 moles of an ideal gas at STP. At STP. The volume will be 0.224 meter cube. Then also solve this for me. If you wish, not me. If you wish to keep 1 mole of an ideal gas in your room, if you wish to keep 1 mole of an ideal gas in your room, how big is the container you are going to use? What is the volume of the container you are going to use? That's what I mean. So the volume of that container you are going to use, if you wish to keep 1 mole of an ideal gas at STP in your room, if you wish to keep 1 mole of an ideal gas at STP in your room, how big is the container you are going to use. So the container will be equal to 0.0224 meter cube. This is the volume of the container we are going to use. So also try and solve that to see what you are going to do. Now, we want to look at pressure exerted by an ideal gas placed in a cube. That's the next thing we're going to look at. Pressure exerted by an ideal gas placed in a cube. That is the next thing we're going to look at now. Pressure exerted by an ideal gas placed in a cube. Now, let's assume we have a cube. Let's assume we have a cube, or we can draw a cube. Let's assume we are having a cube. So we are having a cube. So we are having a cube. With these respective directions. Or let me use this inner side. Let me use the inner side. Let me call here the y. We call here the x. Then here will be the z. Now this will not be seen again. This may not necessarily also be seen. So let's say we have this cube here. And inside this cube, we have numerous molecules of an ideal gas placed inside the cube. How am I going to calculate the pressure exerted by the ideal gas inside this cube now? Now let's draw the side. Remember, for a cube, all the length of all the sides are the same. You know that. The length of all the sides of the cube, they are the same thing. So the lengths are the same. Now we have the x direction, y direction, and z direction. We have the x, y, z direction. So this particular, the gaseous molecule inside this cube, they are either going to move with velocity to the x direction, or they move velocity to the y direction, or they move velocity to the what? Z direction. I don't know if you can get it. If you place the gas inside this place, it's either they will move this way, or move this way, or move this way. Any of them, because they move in the constant random motion. Now we are going to assume that we are having a gas moving in this x direction. We're going to move in this x direction. We're going to assume that we are having a gas moving in the x direction. To this side and the other side and the x, that is parallel to this it is moving parallelly to that x direction, or moving the x direction. So if this gas is moving in this direction, we're going to have velocity x to this side, velocity x to this other side. Now remember, if a gas moves to this side, we hit this wall, this part, this face. If you hit this face, you go back, hit this face again, come back, hit this face, keep on hitting. That will be by the something like caster random motion. We bombard the wall of the container, it collide the wall. They constantly collide with the wall of the container. The container also collide with themselves. Now, let us look at one molecule moving in the x direction. That's when we have one mole of this, just one molecule, not one mole, just a particular, just one particle. That's called molecule. Just one molecule of this ideal gas moving in this x direction. As we move in the x direction, if we move to this side, we cover this distance, we hit this side, move back again, cover the same distance, hit this side again. Let's say you move to this side, hit this wall, move back, hit this wall again. What will be the change in momentum? Remember momentum is equal to what? Momentum is mass times what? Velocity. I don't know if you can remember that. Momentum is mass times what? Velocity. So momentum to this side, when the body is moving to this side, the momentum, that's why P1 will be the mass times the velocity of this body moving to this side, which is the Vx. Then, if the body is not moving to this side, we'll be going toward the left hand side. Remember, for the right, what were the resolving forces? We are going to, let's call the right now positive, then we are going to the left, will be negative. So we'll call that P2. That will be minus Vx now, because it's not moving to the left hand side. You can just say, this one is P1, this one is P2, depending on the side we are taking. There's no problem about that. Or we can just say, okay, the P1 is when it's going to this side. When we go to the left, this one will be negative. This one will be negative. Then the P2 is when we go to the right now, we hit this side, so it will now be positive. Anyone you like. There's no problem about that. So when you know what you are doing, that's the major thing. Then the change in momentum will now be P2 minus P1, which is mvx minus the P1 is m minus mvx. That will give us 2. Okay, let me just finish everything. mvx minus plus mvx. That will be 2m v to the s direction. So this is the change in momentum. And remember that from Newton's second law of motion, that means these gases obey Newton's second law of motion. From Newton's second law of motion, the rate of change of momentum must be directly proportional to what we call force. So change in momentum, the rate of change in momentum means when you divide change in momentum by time, that's the rate of change in momentum. You tell us that force is equal to change in momentum over time. That's what I'm trying to say. From Newton's second law of motion. Or impulse is equal to change in momentum. If you check our laws of motion we did, the thing is there. So this one will be, this change in momentum now, 2m Vx over t. Now, there's something very, very important that you should take note of here. That remember that velocity is equal to distance over time, or speed is equal to distance over time. That's what is speed. Speed is equal to distance over time. Now, what is the distance covered by this distance level? It moves from here to here at the first place. Or it moves from here to here at the first place, then return back again. So if you move from here to here, then cover L. If you return back again, cover L again. So the total distance will now be L plus the second L, which is 2L. That is the total distance covered by this distance molecule that move to this side and come back again. So the total distance is 2 L, then over. Remember I was talking about the velocity to the S direction over T. So from here now, we bring this T here, bring the Vs there. Just multiply T to this place, then Vs to this place. So that T will now be 2L over Vx. So that we put it there. So that our force of this gaseous molecule moving in that S direction would be 2M Vx over what is our time? 2L over Vx. If this Vs go and multiply, this Vs now move to multiply this upper side. We now have 2m Vs squared over 2l. This we cancel this, then we have m Vx squared over what? L. That's what we are going to have. That's what we're going to have. Now, this is the force. This is the particular force. The gaseous, a particular one mole, just one mole of the gas moving in this direction has just one mole of the gas. Now remember we have 3 directions here. We have 1, 2, 3 directions. Number 1. We have numerous moles of any gas here. Now for n numbers of molecules, like for all the numbers of molecules moving in the direction, that's what I'm trying to say. For all we don't know them, why we call it n numbers? We call it n. Let's call the numbers of molecules moving in the direction. Let's call it n. So for the total number of molecules now moving in the direction, the force they are exerting will be the total number times this just one mole, which is this over n. That's what I'm going to have. That's the total number of molecules moving in the x direction. Now, for the number of molecules of this gas moving in this cube now, that's what I want to look at now. Remember, when we are looking at total numbers of molecules, then we now take the total velocity of that they are using. Remember, if number 1 is using this velocity, number 2 is using this velocity, number 3 is using, they might not be having the same velocity. All the molecules of this gas moving in this direction will not be having the same velocity. So what we do to get the proper velocity now, we will take the mean of all of them, of all the velocities moving in this S direction. When we are taking the total numbers of molecules in this direction. So look at this now, what I'm just trying to say. Remember, this was just for one mole. If we want to take the all the molecules, which is n in numbers, we don't know the number, let's say 20 numbers of molecules of a gas, I don't know, we don't know the numbers of molecules, but let's call it n. Then we take the mean of all their velocities, which is, we don't put bar here. So that is the mean velocity of all the numbers of molecules moving in the s direction. Now, the force exerted by the gas placed in the cube now, using the velocity, when we are considering the velocity of the gas, and we don't know where they are even going, whether they are going to the x, whether they are going to the y, whether they are going to the z. The total velocity of this gas will be equal to velocity, okay, let me square it, this one is having squared. Velocity to the s squared plus velocity to the y squared plus velocity to the z squared. This is the total, because some are moving to the x, some are moving to the y, some are moving to the z. So the total velocity of this gaseous molecule now placed inside this cube will be the velocity of the gases moving to the s plus the velocity of the gases moving to the y, the velocity of the gases that used to move to the what? Z direction. Now, because of they move in a constant random motion, we can assume this Vx, Vy, Vz to be the same. Assume them to be the same thing. So if Vx, Vy, Vz are the same, so we should say if Vx, this Vx is equal to this Vy, is equal to this Vz, then each of them will now be equal to 1/3 V squared. How? Because if this and this and this are the same, let's say they are the same thing now. What do? This plus this will be 3V squared. Divide both sides by 3. One of them will be this divided by 3. So I will just say, now this is the average. That is the average. We are taking the average. Total number of x, we take the average. Total number of y, we take the average. Total number of z, we take the average. What do you mean of average? The average of all the velocity moving in the s, all the velocity moving in the y, all the velocity moving in the z, all the gases moving in the x, velocity to the s, into the y, velocity to the z, add everything together. So the next thing, if we assume the velocity to the x, y, and z to be the same, all their average velocities are the same because they move in a constant random motion, then if this and this and this are the same thing, you add this, you have 3 of them. So one of them will now be this divided by 3, which is V bar squared over 3. So the force exerted by this ideal gas moving this cube down will be N over T M V bar squared over N. This is the force. Where this V bar squared is called, this V bar squared is called the mean squared velocity. This V bar squared is called what? The mean squared velocity. The mean squared velocity. And it's different from mean velocity, called the mean squared velocity. The mean velocity, the mean velocity is equal to the V1 plus V2 plus dot 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 until you get to Vn divided by n. This is how you calculate mean velocity. That's how you calculate mean velocity. Then this other one, that's root v squared velocity. You have a way of also calculating it. Now take note of this. This is called mean squared velocity. That's what we call it. That's mean squared velocity to the x. So mean squared velocity of just a particular value. This one is not even mean squared because we are looking at 1. It will be mean when we are at 1, 2 and above. We don't find mean of one thing, average of one thing. Average is when you have add the total divided by 2. So we call this one mean velocity that has squared or mean squared velocity. So it's mean squared. All these ones are mean that has. This one is average squared. That's what we mean by. Remember in statistics, average and mean are the same. Then there's another thing, root mean squared. We call it root mean squared. It's when you square the mean velocity squared. So you take the root of this mean squared velocity. That's what we call it. You take the root of this mean squared velocity. Then we now have what we call root of mean squared velocity. So we call it root mean squared velocity. So if the mean squared velocity is something like this, look at what we mean by the mean squared. You take mean squared. This mean squared means that mean squared means when you square the first velocity plus when you square the second velocity plus dot dot dot. When you square the last one divided by the last number of mean squared velocity. Then this root mean squared now will be when you square this one. which is something like this. The root mean square will now be something like this. When you take the square root of everything here, that's what we mean by root mean square. Velocity. Root mean square. Just square everything, add it together, and divide it by the total number, and then take the square root. That's what we mean by root mean square. But mean velocity is when you add all the velocity together and divide by the total numbers of velocity. So this n and this one are not the same. This one is numbers of molecules there. Then this n is numbers of velocity there. That's how we do mean. Mean means total number added together. That is, add everything together and divide it by the total number. That's what we mean. Take note of that. Then take note of this one. It's very, very important. Now, remember that pressure is equal to force over area. I don't know if you can still remember that. We are going somewhere. Remember, we are this pressure exerted by the gas placed in the cube. Pressure is equal to force over area. Now, let's go back to this place. Or let's go ahead. Let's go back to the x direction. Right now, the component of this x in terms of the general velocity is v bar square over 3. That is this vs. This vs square. That is v bar s. That is vs bar square. So it has v bar square over 3. That is total velocity divided by 3. Because of the 3 faces that are there. So let's go back to that vs square, to the s direction. Now look at this s direction now. What area is this gas going to hit? It's going to hit this area, that is this surface. It's going to hit this place. That's just going to hit. And what's the area of this place? The area of this place that is going to hit is length times breadth. And this length is TL, the breadth is TL, or height times this breadth. So since everything is equal to L times L will be what? L squared. So you're going to have the force exerted by the gas divided by L squared. That's what I'm going to have. That's what I'm going to have. Then, now, we are not going to generalize it for the total, like when we are not looking at the pressure exerted by the gas moving inside the cube now. So that we looked at. So we are not going to, if you are using just the s direction, we use this total number of velocity moving in the s direction, we use this force. If it's just one particular gas in the moving in the s direction, pressure exerted by that gas, we use this. But we are looking at the general, something like velocities of the gaseous molecules moving inside the gas, we use this. Then we are going to have n over 3 v bar squared over L, then divided by L squared. That's what I'm going to have for the pressure. That's what I'm going to have. That is pressure exerted by this ideal gas placed inside this cube now. Then, if you move this one 2 times, then you take the inverse of this other one. The inverse of this other one, which is 1 over L squared. So this one multiplying this, you're going to have n over 3 v bar over, this time you're going to have L cube. And L cube is the volume of a cube. Volume for a cube is equal to L cube. That's the volume of a cube. That's why some books don't use V to represent this velocity here. They do use C. They use C to represent the velocity. The Vs, Gy, Vz, they use U, W, ox, or W, U, and V. Anyhow they do it, but it's still the same C. So, since L cube is the volume of a cube, so we're going to have, remember this one is having bar. We're going to have n over 3 mv bar squared over V. So this is the pressure exerted by the gas placed in this cube. This is the pressure. Pressure exerted by the gas placed in this cube. Now we are still going to, we are still moving. So what you have to do, take note of the definite equations here. So this force, as a function of time, this force of all the molecules moving in the s direction, this force of all the molecules moving in the cube. Then this force, this pressure exerted by the gas placed in the cube. Now, what is the meaning of n? What is the meaning of this one? What is the meaning of that n? That n is the total number of molecules moving in the cube. What is the meaning of n? N is the mass of the gas. So the total number of molecules times the mass of one gas will be the total mass of the gas. Or the total mass. Not polar mass. For example, I said each molecule, they are identical. They have mass of 1 gram. We have 20 molecules there. So how many? What's the mass? What mass are we having? That's the mass of all of them added together, or the 20 times the mass of one of them and give us the total mass. That's what I'm trying to say. So this mm denotes the total mass of the gas. That denotes what? Total mass of the gas. So we can also say P is equals to 1 over 3 nm over V times V bar squared. Now, what is this one? Is total mass. Now, total mass divided by volume. What are we going to have? Total mass divided by volume. That is the same as density. Because density is mass over volume. So, this total mass over volume will be density. So, we have 1 over 3 times density times V squared. So, this is P as well. This is the pressure exerted by an energy gas placed in the cube. Now, what about, take note of this one, very, very important. What about if I want to make density? So, a formula. If I want to make this density the subject of the formula, then the density will be 3 times P, the pressure, divided by the V bar squared. That is mean squared velocity. The mean squared velocity. What about if I want to find this, to make this mean squared velocity formula, then the mean squared velocity will be this one, we have 3P over the density. I'm going to find this one. When you square this mean square velocity, that's when you take the square root of this. I take the square root of this one, I'll take the square root of this, then I'll have root mean square velocity. Remember, root mean square means when you squared the mean square velocity. So that will be the square root of, remember this and this are the same, I already showed it there. You have 3P over this. That's what we will have. So take note of this, very important. Take note of this, very, very, very 100% important. Very, very important. So all those formulas we are deriving, they are very, very important. Now let's look at furthermore. Let's look at average translation. How to move out our average translational kinetic energy now. How do we get our average translational kinetic energy? How do we get that? Our average translational kinetic energy. Now, you can record that from there, from this place. Not from here, from this place. You can record that P, which is equal to 1 over 3. Okay, let me just say, 1 over 3 nm V bar squared over what? Over volume. Can you remember this? Yeah. Remember this. If I move this V to this place, I'll have PV is equal to 1 over 3 nm V bar squared. And this PV is still the same thing as from the general equation of ideal gas. The equation of ideal gas, we said PV is equal to nRT. I don't know if you can remember that. The PV is equal to nRT. So if I move on to this one, I'll have PV to be equal to this. I just have this nRT as well. So that we'll be having we can say our 1 over 3. Now look at something. Look at what I want to do now. Half n by mv squared. Remember, half mv squared is equals to velocity, kinetic, that's energy, kinetic energy. Now, if I want to get the average translational kinetic energy of this gas now, what I'm going to do, I'm going to introduce something 1 over 2 mv squared here. That's what I'm going to do. I'll introduce 1 over 2 mv squared here. What I'm trying to say. Look at this. I want to write it on out. I want to write this out. I have mv squared. What I mean is 1 over 2 of this mv squared. So what will I do? I will come back to this 1 over 3 n and multiply everything by 2 over 1. So that this 2 will cancel this and it will still be the same thing. So if this 2 move to this place, I will have something like this. I have 2 over 3 n. That's what I'm going to have. Then, or you can say, divide this one by 2 and multiply this one by 2. These 2 will cancel this. It seems to be the same thing. It seems to be the same thing. That's what I'm trying to do. So I have to get 1 over 2 here. To get 1 over 2 here. So I'm going to have this to nRT. It's called to what? nRT. So if I move this small n to this place, I divide both sides by n, divide side by n. This n will cancel this. This one will be called KE. Call it average translation because kinetic energy is mv squared. Half mv squared is kinetic energy. So I'm going to have 2 over 3 Then numbers of molecule divided by numbers of mole is Na, which is Avogadro's number. Numbers of molecule divided by numbers of mole is equal to Avogadro's number. Then half mv squared is equal to kinetic energy. It's equal to kinetic energy. Then everything here will now be equal to ROT. Then from there, I will move this 3 to this side, move this one to this side, then divide both sides by Na. I'll move this 3 to here, then this 2 will come down. Just like that, multiply 2 times 1, 2, 3 times this. I have Ke to be equal to this one, this is 3, this one will come down, that is over 2. Just like I multiply both sides by 3 over 2, that's over 2. 2 cancel 2, 3 cancel 3. Then this Na we also move downward. We have R over Na times T. Now, R over Na is called Boltzmann constant. That's what we call it. Boltzmann what? Constant. Boltzmann constant. Boltzmann constant. We know by K. Boltzmann constant. So our Ke now will be 3 over 2 Kt. Where K, I hope you are enjoying this derivation. Where K, where this K you are seeing here, not this K is directly equal to 3 over 2 Kt. That K there is called Boltzmann constant. Boltzmann constant is approximately 1.38 times 10 power minus 23 joules per Kelvin. Joules per Kelvin. Why is it joules per Kelvin? Because this one is in joules, temperature is in Kelvin. That's why it's in joules per Kelvin. Or you can also say this as Na is equal to R over Na. R over what? Na. I know you don't know of Avogadro's number. So divide 8.314 by Avogadro's number. Check if you are going to have this. Check if you are going to have this. Check if you are going to have that. So that's what we will be having there. So let's look at some questions now under what we are doing since to see what we are going to have. Alright, let's look at this question. Look at this question. 3 molecules of ideal gas. 3 molecules of ideal gas have velocities. 3 levels, that is 300 meters per second, 500 meters per second, and 700 meters per second, respectively. 3 molecules of ideal gas have velocities 300 meters per second, 500 meters per second, and 700 meters per second, respectively. Find number 1, V bar, number 2, VROMX, number 3, the density at STP. Find V bar, VROMX, density at what? At STP. Now, I told you guys that first one, V bar is equal to V1 plus V2. So you get to what? The last one, then over the total number. So what is the first one here? V1 is V1. This V2, this V3. So our V1 is 300 plus V2 is 500 plus V3 is 700. Over how many of them do you have? 1, 2, 3. That's it. That's all. Then the next thing will be, if you add it together, you're going to have this plus this plus this. Divided by 2 will be 500 meters per second. That will be the mean velocity. I know V bar. Then the next one is, what is VRMS? Root mean square velocity. Is V the square root of what? Square root of V1 squared plus V2 squared plus until what? Get to the last one and square it divided by the total number. So we have the square root of, what is the first one? We have 300 squared plus 500 squared plus 700 squared divided by 1, 2, 3. So this will give us approximately 526 meters per second. That's what we are going to have. Now, what is now the density at STP? What is density at STP. Remember from the calculation, from the stuff we did, we said density is equals to 3p over what? Over v squared. That is the root mean squared velocity. Without taking the square root. So you just say this one is empty as v RMS squared. Same thing. You check. If you like, go and solve this out. Don't stick square root, don't do it and solve it out. You have the same thing. I'm saying now. So this will give us at STP. Remember at STP. That is the last one. At STP, our pressure is what? Pressure will be what? 1.013 10 power what? 5 Pascal. Remember that. So that's why I say STP. So that you know that the pressure is that. Pressure is that at STP. Temperature is 273 Kelvin. So we have 3 times 1.013 10 power what? 5 over 526 squared. So this one will give us 1.1 kilogram per meter cube. That's the density we will have. Density is in mass over volume, kilogram per meter cube. Approximately 1.1 kilogram per meter cube. That is the density we are going to have. Now let's look at another question. To guide this, look at another question. Calculate the average translational kinetic energy of a gas at 300 Kelvin. Calculate the average translational kinetic energy of a gas at the temperature of 300 Kelvin. Remember that average translational kinetic energy is equal to what? 3 over 2 kT. So in case what? 1.38 times 10 power what? Minus 23. So you're going to have 3 over 2 times k, which is 1.38 times 10 power minus 23 times k, which is what? T, which is 300. So if you do that very well, which is equal to 6.21 times 10 power minus 21 joules. That's the average translational kinetic energy I don't have. So just 3 over 2 kT. K is Boltzmann constant, which is this. This multiply temperature with 300 Kelvin. This you are already going to know. When the temperature is not in Kelvin, ensure you move the temperature to Kelvin. In this topic, all the temperature should be in Kelvin. Take note. All the temperature should be in what? In Kelvin. Now let's look at distribution of molecular speed. Now we have what we call the most probable speed of a gas, most probable speed of a gas. We have the average speed of a gas. We want to give the average speed that we have in here in terms of some constant like Boltzmann constant or molar gas constant. How do you give it? The mass of the gas. We want to something like rewind this root mean square speed and average speed in terms of some constants that have to associate with gaseous molecule, like all this molar mass of the gas, the molar gas constant and the Boltzmann constant. We want to like rewind the root mean square speed and the average speed and the most probable speed. Then we'll look at some transport properties of the gas, like mean free part of the gas, viscosity of the gas, thermal conductivity of the gas, and the other one, which is the coefficient of diffusion of the gas. Yeah. Alright, now we want to look at the distribution of molecular speed. The distribution of molecular speed. Now, remember when we're looking at pressure exerted by any gas placed in a cube, we're looking at the velocity of a particular molecule of a gas inside a cube. Where we got something that we called the average velocity. We also got a velocity that we call the root mean square velocity of that gaseous molecule. Now, we want to also look for the average velocity and the root mean square velocity of a gaseous molecule moving as a function of temperature. That's how do molecules respond to change in temperature and the rest. So, in our first formula for the first one we did, the temperature inside, we're just looking at we're looking at average velocity, R velocity divided by the total number, root mean square velocity, we're looking at function of pressure and density. But now I want to look at the function of velocity and speed and temperature. How the gaseous speed responds to temperature, if temperature something like and so on. Now, the first velocity we are going to look at now from this distribution is the one we call the most probable speed. The most probable speed of a gas. The most probable speed of a gas. That's what we call it. The most probable speed of a gas. Now, the most probable speed of a gas, the most probable speed of a gas is always defined as the root of RT over, root of 2RT over capital letter N. Root of 2RT over capital letter N. Now, this can also be given as, we can also say the most probable speed of a gas is equals to the square root of 2kT over small letter n. Now, what is the difference between this formula and this formula? Now, if I find the square root of 2, I'm going to have 1.4. So I can also say our CMP is equals to 1.4, the square root of either 2RT over capital letter M, or then the 2 will not be there. Because root 2 is already 1.4. Then RT over capital letter M or KT over M. Let me just use this. RT over capital letter M or KT over small letter n. Now, what's the meaning of capital letter N? What's the meaning of small letter n? Now, remember we have what we call mass of a body. Mass of a body. Mass is the quantity of matter a body has. Now, this small letter m is mass in grams or kilograms. Then, this capital letter M is called molar mass in grams per mole. So, this is molar mass, while this one is just mass. So, take note of that. So, anytime you hear molar mass, or if you know the name of the gas, for example, what is the molar mass of oxygen gas, which is O2. The molar mass will be 32 grams per mole. Then, I can give you a gas that maybe smoke. I'll tell you, look at the mass of the smoke, not molar mass. There's no between just mass and molar mass. This mass is in grams. It's in grams. Then why this other one? This mass is in grams, which is much of matter the body has. Then this other mass is molar mass in grams per mole. Grams per mole. So take note of that. It's very, very important. So this is the formula for the most probable speed of a gas. The what? The most probable speed of a what? Of a gas. Now, the next one we're going to look at is the average speed of a gas. The average speed, CAV. The average speed of a gas. Now, the average speed of a gas is checked. The only function is a function of temperature. This is a constant. Only this mass sometimes may change somehow. In most cases, the mass is still a constant. Both this mass and this one, they are constants. The only thing that will change here is temperature. Then, if I measure oxygen now, oxygen gas O2, the molar mass will be the same. Whether I'm measuring oxygen gas O2, the molar mass is always 32 grams per mole, 2.0 something grams per mole. That's how the thing is. Nitrogen has the same molar mass everywhere. That's what I mean by there will be something like some constants. But the temperature can change. It has a temperature of 35 Kelvin and so on. Then we have the average velocity, average speed or average velocity of a gas. The average velocity of a gas. Now, from the first one we did, we're saying we said root mean square velocity is equal to the square root of so and so. Now, if you solve that formula for that, you're going to have the average speed. No, not root mean square. Now that is for root mean square. That is for average speed. From this distribution now, what we're doing, distribution of molecular speed. Now, from this distribution now, we discover that the average speed of a gas is the square root of 8 RT over pi times capital letter M, or the average speed of a gas is the square root of 8 kT over pi times small letter m. Now you can also still remember that this small letter m and this capital letter m is very utility too. I don't want to tell you that now. So you can also find the square root of 8 over pi. That can be 1.6. Then you don't take RT over n or KT over small letter m. That is still possible. Then we have the last one. We have 3 of them. The most probable speed, the average speed. The last one is the root mean square speed. Take note, this C denotes speed. I'm not using V here now because they are doing distribution of molecular speed. Then the root mean square speed of a gas. If you will find the root mean square speed from that density and pressure, you are still going to have what we are having here now. The root mean square speed of a gas is equal to the square root of 3 kT. Okay, let me start from R. 3 ROT over capital letter M, or the root mean square speed of a gas is the square root of 3 kT over small letter m. This m is in grams or kilograms and so on, while this capital letter M is in grams per mole. Take note of that. I'm going to solve a typical question. Now. I will use both formula to solve the problem. And you will check whether we are not going to have the same answer. That's how it is. Now, let's look at transport phenomenon. A transport phenomenon of a gas. Transport properties of a gas. Now, before we look at the transport property, there is something very important during the movement of a gas. During what? The movement of a gas. Now, we'll be looking at, we are not going to gradients. So we have like concentration gradients, temperature gradients, and so on. So the first one now, the first thing we're going to look at before we take all these phenomena is what we call the mean free path of a gas. Mean free path of a gas. The mean free PATH. The mean free path of a gas. Now, what do we mean by the mean free path of a gas? Now, the mean free path of a gas is defined as the average distance traveled by a gaseous molecule before colliding with another gas, or the average distance covered between a successive collision. Before you have a successive collision. So the mean free path of a gas is the average distance the molecule will travel before colliding with what? Another gaseous molecule. And it is defined as, we use lambda or air. This mean free path, this is lambda. Now you use lambda or use air, anyone you like. Is equals to 1 over root 2 pi d squared times n prime. Root 2 pi d squared times what? N prime. Now, what is the, or we're going to say mean free path is equals to RT over root 2 pi d squared NA times P. NA times P. Or we can also say mean free path is equals to R over NA. Remember it's equal to K, which is Boltzmann constant. Then times T over the square root of 2 pi d squared times P. Now, look at it. These are the 3 formulas we have for now for mean free paths. Now, you know RO is molar gas constant, which is 8.314 joules per mole Kelvin. K is Boltzmann constant. What? I've mentioned that before. Boltzmann what? Constant, which is 1.38 times 10 minus 23 joules per Kelvin. Then this NA here is called Avogadro's number. Avogadro's number, which is per moles. Then P is pressure. And D, this D you are seeing here, is called collision diameter. That's what we call it. Collision diameter. Pi is 3.142. K is Boltzmann constant. And T is temperature. But anyway, you see T here, 1, 2, 3, all those T are seen here. They represent temperature in Kelvin or thermodynamic temperature. So this temperature should be in Kelvin. This D should be in meters, which is called collision diameter. You write it down. So it means collision diameter. P means pressure. That's the meaning of P. P means what? Pressure. Then this small, we have small letter N here. Now, what is the meaning of this small letter N? Now, this small letter N is called numbers of molecules. Not numbers, okay? I can call it numbers of particles. The unit is in molecules, not mole. I told you that day that mole is not abbreviation for molecules. Amount of substance is measured in moles. Moles is the unit for amount. Remember the fundamental unit we have. Moles for amount of substance, or amount of substance in moles. So moles is the SI unit for amount of substance. Then molecule is just something like we count it as numbers. Just a numbers of molecules. So this one now is numbers. It's just like particles. Something how we call it. We said gaseous. Gases are comprised of particles that we call molecules. So how many particles that we call molecules are there? That's what you have here. Numbers of particles, which is in molecules. So this we can also call it so numbers of molecules. That's the number of particles we have there. So numbers of molecules, numbers of molecules. But this one is in per volume. Per what? Volume. This one is numbers of particles per volumes, or numbers of molecules per volume. That's what we have here. That is one. That's M prime. Then I told you the meaning of this. This is root mean square speed. This is average speed. So it's most probable speed. So ensure you just write everything down. Then the next thing I'm going to look at now, we're going to look at the viscosity. That's the first thing I'm going to look at for this transport property or transport phenomenon. We're going to look at the viscosity of a gas. The viscosity of a gas. That's the first one. Viscosity of a gas. The viscosity of a gaseous molecule. Let's look at that. Now, viscosity of a gas. The viscosity of a gas. Now, when we are mentioning or speaking of the viscosity of a gas, what are we actually saying? Now, we're going to describe gaseous molecules now in terms of we'll get to velocity gradients. Now, this viscosity of a gas actually speaks on velocity gradients. Now, these are gradients. All those transport phenomena bring gaseous molecules to study of gradients. We have velocity gradients, temperature gradients, and the rest. Now, viscosity actually responds to the velocity gradients and the rest. Now, what's the meaning of viscosity? How do we define viscosity? Now, viscosity is the frictional resistance that a fluid in motion will offer to an applied shearing force. So, what we ask is gases, do we call gaseous molecule or gas? Can we call a gas a fluid? Yes, in fluid mechanics, gases are part of fluid that we look at. The frictional resistance that the fluid in motion we are part what? To an applied shearing force. Why the coefficient? Remember I said, why the coefficient of viscosity? Why the coefficient of viscosity can be described as the force per what? Per area, per velocity gradient. So this talks about actually velocity what? Gradient. So that will be equal to 1. If you want to describe it in terms of transfer property of a gas, we said the coefficient of viscosity is equal to 1/3, that is 1/3 of L times V bar times rho. Where L is equal to lambda, which we call the mean free part of the gas. So we got the mean what? The mean free part. So I told you before that we can either use L here or lambda. So this is the mean free part. Now V bar, this V bar is called CAV. So this is the average velocity of the gas, or you can write it this way, CAV. So you can also write it this way now. You can also say this is equal to, this lambda is equal to 1/3 lambda CAV times density. Now this density is mass times N. Talking about that. Now this is the mass of the gas. Then this is numbers of, something like numbers of particles in per. Okay, how many gaseous molecules do we have there? in per volume. So if you now take mass over volume, so this gives us, now if I write now, remember there was something we did before. There was something we did before. And I told you, M times N is called total mass. You guys remember that? Then this one, this N here is not just ordinary mass, but that is in per volume. So if we now take that volume which is in per, we now have our density out. We now have our density outside. So that is the definition of the resistance. So this is the density, this is the density, this is the density, the average speed, the mean free path, and this is just 1/3. This and this are actually the same thing. So this is how we describe the velocity of a gas in transport properties. So let's move to the next one, which is thermal conductivity of a gas. The thermal conductivity of a gas. Now, what's the meaning of thermal conductivity of a gas? When we look at thermal conductivity, what are we actually seeing? So let's go there. Now, this thermal conductivity talks on the rate of energy transferred. The rate of, remember, thermal energy. I don't know if you can still remember that. Is heat energy. So this is the rate of energy transferred per unit area, per unit temperature gradient. So it actually throws light. This thermal actually tells us about the temperature gradient of gas. So while the first one we did, which is viscosity, was dealing with velocity gradients, this one is actually talking about temperature gradient. And it can be defined as K is equal to 1/3, then N times V bar, density times CV. Now, what's not CV? What's not CV? Because I already explained this corresponds to this. You can see that. Everything you see here corresponds to this, but the same thing. But this CV is the only different here. Now, what's going on that CV? Where this CV is called specific heat at constant volume. That's what we call that. The specific heat of that gas at constant volume. Let's know this one. Specific heat at constant volume. The specific heat at constant volume. So you take note of that. It's very, very important. Now, the last one, we have three of them. The last one we're going to look at now is diffusion coefficient of a gas. The diffusion coefficient of a gas. Now, when we are dealing with diffusion coefficient of a gas, what are we actually saying? We are talking about diffusion coefficient of a gas. What are we actually saying? Remember what we are doing here? We are doing transport phenomenon of a gaseous molecule. The transport property. Transport. I don't know if you can still remember transportation. Remember, we went to close services from one point to another. When the gaseous molecules are moving, right, things you get, you have viscosity of that gas, you have the thermal conductivity, the rate of energy transfer, per unit temperature, per unit temperature gradients. And we also look at the diffusion coefficient. Remember diffusion in biology those days. The diffusion coefficient of a gas, and that's what we want to look at now. So, how the gaseous molecule diffuse. So, what is the diffusion coefficient? Now, this diffusion coefficient is the rate of particle flux per unit area, per unit density gradients. Per unit area, per unit what? Density gradients. Now, this diffusion coefficient also throws light on concentration gradients. Concentration gradients. So we said it's the rate of what? Of particle flux per unit area, per unit density gradients. And it can be defined as D is equals to 1/3 L times V bar. 1/3 L times V bar. Where this L is mean free part, there's no density here. No density here. I think it's density graded there, so no density in this place. No density here. So when that what's it called? L is the mean free part, and let me just put the L here so that it will not be confusing. So just put L here so that you know that. So it's either L or this, either L or this, either L or this. Anyway, see L here, it's actually talking about what's it called? Mean free parts. Mean free parts. Now, let's look at this question. Obtain the average translational kinetic energy. Question 1. Look at questions now. Let's solve questions now. Obtain the average translational kinetic energy of a gas. Obtain the average translational kinetic energy of a gas. Just molecule at a temperature of 27. Okay, let's leave that. Temperature of 25 degrees Celsius. To calculate the average translational kinetic energy of a gas at a temperature of what? 25 degrees Celsius. Remember we said average translational kinetic energy is 3 over 2 kT. You can say remember that. 3 over what? 3 over 2 kT. So, if you do that, remember K is a constant that we call Boltzmann constant. Boltzmann constant is 2.3, okay, 1.38 times 10 to the minus 23 joules per kilogram. So, if you solve this, we have 3 over 2 times 1.38 times 10 to the minus 23 times temperature, which is in degrees Celsius. So, we are going to move that temperature to Kelvin now. Now, the temperature will be 25 plus 273. That is 298 Kelvin. 298 what? Kelvin. That's how to convert from 0 to maybe add 73. We have 298. So this will give us 6.2 times 10 to the minus 21 joules. That is the average translational kinetic energy of that gaseous molecule. Now let's look at more questions under what we have just explained to see what we have just explained to see what we are going to get. Alright, let's look at this question. Look at this question. Calculate the average speed of nitrogen molecule. Calculate the average speed of nitrogen molecule. Calculate the average speed of 1 mole of nitrogen molecule of mass 28 times 1.66 times 10 to the minus 27 kg is the mass of 1 mole of nitrogen molecule of 28 times 1.66 times 10 to the minus 27 kilogram. That's the mass. At a temperature of 300 Kelvin. At the temperature of 300 Kelvin. Now, I can also ask you to look for the average translational kinetic energy of this molecule at this temperature. You should know how to solve that now. K is equal to 3 over 2 kT. Now, what we're looking for is average velocity. I told you it's a formula for average velocity with respect to what? Temperature. And it's that CAV is equal to what? The square root of 8. Look at kilogram. The mass that was given is in kilogram. So we're going to use the 1.5 K. If the mass is in grams per mole, which is molar mass, we use the 1.5 R. So if the mass is in kilogram, we use 8 kT over small letter n. So now give us, okay, pi. Remember this pi again. Now give us the square root of 8 is 8. Remember K is Boltzmann constant. K is 1 point. It's a constant number. Times 10 to the power minus 23 joules per Kelvin. Joules per Kelvin. Remember that is the value for K. That is the constant value for K. So that is 1.38 times 10 to the power minus 23 times, what about the temperature? The temperature is what? Is 300. Then divided by pi times the mass. What is the mass? Mass is 28 times 1.66 times 10 to the power minus 27. So if you solve this very well, you're going to have 476, approximately 476 meters per second. That will be the average speed of the molecule. The what? The average speed of the molecule. Now, look at the question. They mentioned 1 mole of nitrogen gas. 1 mole of nitrogen gas. And we know that nitrogen gas is N2. Just 1 mole. It's N2. If you have so many moles, we will use the numbers of moles to multiply what we have there. Then, the molar mass of N2. What is the molar mass of nitrogen gas? N2. What is the mass of, what is the molar mass of nitrogen? 14. Multiplied by 2. We're going to have 14 times 2, that is 28 grams per mole. That is the molar mass of nitrogen gas. So, for the question down to kilogram, because R is in kilogram, which is joules per mole Kelvin. That joules is in kilogram. Then, moving on, you move on to, don't solve with grams because of that constant there. I want to use, because I've already gotten the answer now. From this first formula. I want to use one that have arrow. This one, CAV is equals to root of 8 ROT over pi times n. I want to use one that have arrow now. Maybe for the molar mass of that nitrogen gas to see if I'll have the same answer with this. This is not the name of the gas. But if it's smoke, you don't know the molar mass of smoke. If you just ordinary gas, you don't mention gas, you don't know the molar mass of that gas. So please, make sure you know what you are doing. So because they mentioned the name of this gas now, I know the molar mass, so I'm really good to go. From the table or from just chemistry, you can get the molar mass of this N2, this nitrogen gas, which is 2 times mass of nitrogen minus 14. 2 times 14 is what? 28. So moving on to kilogram now, divide by 1000, I'm going to have 0.2, okay, 1, 2, 3, 0.028, that is in kilogram, kilograms per mole. So this one is 9 kilogram now. So we're going to use this one that is in kilogram. So we're going to have the square root of 8 times, arrow is, what is arrow? 8.314, 8.314 times temperature is 300. Then over pi times this cabinet, this molar mass is what? 0.028. So if you do that very well, you're still going to have 476 meters per second. Check. Just try and do it to see both of them will not be the same thing. So if I mention oxygen is in oxygen is O2. That's oxygen gas. One molecule of oxygen is O2. So just put O2. That is 16 times 2. That's 32. Put 32 here. But that 32 is in grams per mole. If you want to convert to kilogram per mole, divide it by 1. That is 0.032. Put it here and on it. You're already good to go. So that is how that formula is. But look at this question now. If I ask you, calculate the root mean square. The root mean square speed of a gas. Calculate the root mean square speed of a gaseous molecule of mass 10 raised to the power 16 kilogram. Calculate the root mean square speed of a gaseous molecule of mass 10 raised to the power 16 kilogram. What are you going to do? What are you going to do? You don't know it. They say of a gaseous molecule, there's no name given. But they gave you mass. Don't go and use this. This one have to do with molar mass in grams, but not in kilograms or grams. So what we will do, remember C ROMX is the square root of 3 kT or ROT over M. So K associated with either grams or kilogram. The arrow associated with all these grams per molar mass. So I'm going to use the exact K, 3 kT over M. So this one is the M here, which is the mass of the gaseous molecule. So you just come 3 root 3, K is 1.38 times 10 to the power minus 23. 23 times T. Okay, I not give T the question. Okay, let me finish it. Obtain the root mean square speed of a gaseous molecule of mass 10 to the power 16 kilogram at 350 Kelvin. That is temperature at 350 Kelvin. So temperature is 350 Kelvin over the mass is 10 to the power what? 16. So this will give you approximately 0.012 meters per second. So the gaseous molecule is moving slowly. It moves very slow. Very, very slow. So we're going to have 0.012 meters per second. So another question. Let's go at another beautiful question. Another question. Calculate the root mean square speed. Calculate the root mean square speed. Calculate the root mean square speed. Calculate the root mean square speed and the mean free path of oxygen molecule at 300 Kelvin. Calculate the mean free path and root mean square speed of oxygen molecule at 300 Kelvin. At 300 what? Kelvin. Suppose that the diameter of a typical molecule. Suppose that the diameter of a typical molecule is 2.0 times 10 to the power minus 10 meters. Suppose that the diameter of a typical molecule is 2.0 times 10 to the power minus 10 meters. And there are what? There are 3.0 times 10 to the power 25 molecules per volume present. And there are 3.0 times 10 to the power minus times 10 to the power 25 molecules per volume present. So what will be the mean free part and the root mean square speed of this oxygen gas. So from this question now, remember this is our temperature. So this is the collision diameter. I already explained that for mean free part. Remember the mean free part is equals to 1 over root 2 pi d squared times m prime. Where this m prime is numbers of molecules per volume. This is the collision diameter. So we just going to have 1 over the root of 2 times pi is 3.142 times d is the collision diameter here, which is 2 times 10 to the power minus 10. Then you square it. Then sure you square it is very important. Then you square it. Then times the numbers of molecules per volume is 3.0 times 10 to the power 25. So if you do this, 1 over this times this, you're going to have 1.876 times 10 to the power minus 7 meters. It's in meters. We're looking at diameter. It's in meters. Then the root mean square speed of the gas. Remember, as a function of temperature, root mean square speed is the square root of 3. There's no mass given. But we know the molar mass of oxygen gas. And the molar mass is for O2 is the molar mass of O2 is 32. Okay, times 2 because we have oxygen. Okay, we have 16 for oxygen. The molar mass of oxygen is 16. 16 times 2 that is 32 grams per mole. So we are going to use 32 grams, which is divided by 0.022 kilograms. From being kilogram per mole. We're going to use this one. So that we're going to use ROT now over capital letter M. That is square root of 3 times 8.314. Temperature is 300 over molar mass is 0.032. So this will give us approximately 484 meters per second. 484 meters per second, or 43.5 meters per second. So that's what we're going to have as the root mean square speed of this oxygen gas. So let's look at some other questions now before we call it a day. Let's look at this question. Obtain the root mean square speed of nitrogen molecule. Obtain the root mean square speed of nitrogen molecule. In bracket write N2 of nitrogen molecule. In N, that is bracket write N2 at a temperature of 300 Kelvin. At the temperature of 300 Kelvin. So that's the question. So remember speed. At the temperature we said root mean square speed is equals to square root of 3. Okay, let's check. The mass is not given. We're going to use the molar mass of this one, which is ROT over capital letter N. You can also say V root mean squared is still allowed. 3 ROT over capital letter N. So this one is root mean, they are both root mean square speed. Yeah? So the next thing now we'll do will be, we already know that mass of nitrogen, we have done that before. The molar mass of nitrogen, molar mass of N2 is 28, which is 14 times 2. 14 times 2. So they can also tell you the molar mass of nitrogen is 14. Then molar mass of nitrogen 2, that is N2, will be 14 times 2. That is 28 grams per mole. Divided by 1000, we are going to have 0.028 kilograms per mole. That's what we are going to have. Then after this now, because of this constant, that's why we are converted to a kilogram. The next thing we're going to have the root mean square speed will now be equal to the square root of 3 times this R molar gas was at 8.314 times our temperature is 300, then over nitrogen we said is 0.02, that is 0.028. So after this now, we are going to have answer 570 meter per second. That is approximately, I mean 516 point something. So approximately 517 meter per second. That is the rhythmic square speed. So we have done a lot in this place, and we're going to round up this class here. Though in this side, in this channel, we will still be solving questions regarding this topic, just one question. So let's see how far you have gone. But from what you have been doing since, take note of everything we have mentioned. And the transfer property that talks about all these gradients, also take note of that. The gradients, we have the velocity gradients, we have the density gradients, position gradients, temperature gradients. Also to take note of each transfer properties that talks about each of those gradients. Then, so I'll see you guys in the next class we are going to do. Thank you all for attending this class. God bless you all. In case you don't understand anything, I don't know, comment section or watch this video over and over again. Don't just download the video and leave. Watch it online. That's the image. After watching it online, then you will feel the something like the impact of the video. You can comment. But if you download and leave, you don't know when we'll post other videos. So you watch be watching the videos online, just watch them online. There's no need of downloading them where you can watch them online in that same data. So so that your phone will not be having because even though you download it now, you still delete it. But if you watch it online, you want to watch it again, it will be very, very, very free for you to watch. So see you guys in our next class. Thank you. God bless you.